Welcome to the sixth video on compressible fluid flow. In this video, we'll look at the full form of adiabatic energy equation, and we will also discuss how we can obtain the adiabatic flow ellipse using this full form of adiabatic energy equation. Now, from the steady flow energy equation, we obtain the following relation. This equation represents the steady flow energy equation. Let A represent the static state of a fluid and the corresponding stagnation state be represented by 0A. For a stagnation state, we know that the flow is isentropic process, so Q is equal to 0. There is no heat transfer. It's an adiabatic process. The elevation is same, so the energy terms related to elevation gets cancelled off. It's a simple flow through a 90-degree bent pipe, so the shaft work is also 0. The final velocity at the stagnation state is equal to 0 because the flow has to be decelerated to 0 velocity to obtain the stagnation condition. Applying all these to the steady flow energy equation, we obtain the adiabatic energy equation. Let us refer this to as the first form of adiabatic energy equation. Now, in order to get the different forms, we use the following equation that is used for a perfect gas. The first one, P is equal to gamma RT, is the perfect gas equation. Cp is equal to gamma R by gamma minus 1 is the relation connecting the specific heat at constant pressure with specific heat ratio and characteristic gas constant. A is equal to root of gamma RT is the simplified form of velocity of sound, and H is equal to Cp multiplied by T is valid for a perfect gas. Using these equations, we modify the first form of adiabatic energy equation to arrive at the following final equation. We see that the static enthalpy and stagnation enthalpy terms has been replaced with velocity of sound corresponding to static and stagnation conditions respectively. This form is known as the kinetic form of adiabatic energy equation because the adiabatic energy equation is represented by different velocity terms. Let us refer to this as the second form of adiabatic energy equation. To obtain the next form, we express the adiabatic energy equation of the first form in following manner. That is, we replace the static enthalpy with the product of specific heat and absolute temperature. When the temperature becomes 0, that is, when the temperature becomes absolute 0 temperature, the static enthalpy reduces to 0. This means the entire energy gets converted to kinetic energy of fluid. Remember that energy can neither be created nor be destroyed. It can be only transferred from one form to another form. That means now the kinetic energy of the fluid is maximum because it is equal to the total energy or the maximum energy possessed by the fluid. And the velocity corresponding to the maximum kinetic energy will be also the maximum possible fluid velocity and is also referred to as the isentropic velocity of fluid. At this particular point, we see that the velocity of sound will be 0. This is because we know that velocity of sound A is equal to root of gamma RT. When T equal to 0, then A becomes 0. Now at the point of zero absolute temperature, the energy possessed by the fluid molecules are zero, because of which the vibrations are zero and the transfer of wave from one molecule to another molecule will not be possible, and hence the velocity of sound wave will be also zero. This is the third form of adiabatic energy equation. Now, in order to obtain the next form of the adiabatic energy equation, let us write the first form in the following manner. Let the static condition in the above equation correspond to the sonic state. In such case, the velocity term A and C will be replaced by A star and C star as shown in the third equation. Now, at sonic state, the velocity of sound and velocity of the fluid are equal. So, A star is equal to C star. We can take the term outside and rearrange it in order to get the final form. This, putting all together all these forms, we get the final equation, that is the full form of adiabatic energy equation. This is important because using this we will be able to relate different velocity of sound and different fluid velocities at different conditions and obtain a different kind of relations as required. Now this is referred to as the full form of adiabatic energy equation because this includes the kinetic form of adiabatic energy equation, the condition at maximum velocity, the condition at zero velocity, that is the stagnation state, and the condition at sonic velocity. The condition at maximum velocity also refers to the condition of velocity of sound being zero. Hence, this forms the full form of adiabatic energy equation. Now let us see what is the adiabatic steady flow ellipse. It is also known as Prandtl's velocity ellipse. Consider the following equation that we obtain from adiabatic energy equation. It can be modified and written in the following form shown by the second equation. You see that the second equation represents an equation for ellipse. We can compare it with the equation for ellipse and see that here x represents the velocity of fluid, y represents the velocity of sound, the intercept A represents root of 2h and intercept B represents square root of gamma minus 1 into h0. Keeping this in mind, we will be able to plot an ellipse in first quadrant. Only in first quadrant because we are taking the positive values of velocity of fluid and velocity of sound. And we obtain the following graph. Here, if you take a line passing at 45 degree, it represents the point of sonic flow, that is Mach number is equal to 1. This region represents incompressible fluid flow. This region represents subsonic flow. Then we have the transonic flow followed by the supersonic flow and hypersonic flow. Using adiabatic ellipse, we can represent the different flow regimes with respect to a state coordinate system. Now, what is the advantage of this adiabatic energy ellipse? This gives a relationship between the fluid velocity and velocity of sound and at each and every point. Using this ellipse, we can find out how the sound velocity is related to the fluid velocity. If we know the sound velocity, by plotting it into this curve, we can find out what is going to be the corresponding fluid velocity, and from that we can also evaluate in which flow regime the corresponding values lies in.